studied on dual spaces in the earlier class. Today, we will continue to review the background for the linear modeling. Okay, now we start from the partitioned matrix. And you know what's the definition of partitioned matrix. And the partition matrix is a matrix which has blocks here and there. And so we can simplify our computation of the matrices when we have a structured block matrices. But nowadays, our computational ability is getting higher and higher. So we the importance of the study on those block matrices is getting less and less. Okay, so now those computational skills deals with the many problems that was treated with the theory on the block matrices. So now you are in the better situation. And you know what's the submatrix? And the principles of matrix is a matrix like this. This 1 by 1 matrix, and this 2 by 2 matrix, and this 3 by 3 matrix like this. Those are the principles of matrices. The example. Deleting. And partition and multiplication and partitioned matrix. Okay, and what it was dealt there can be rewritten in this way. So the following notations will help you to understand what we have learned. First, this notation Q's of R and M is a set of strictly increasing sequence of length R from the set of positive integers from 1 to m. So an element in this set is a sequence of strictly increasing numbers chosen from this set. Okay, and the cardinality of the element in here is R, and the cardinality of this set itself is same as the M choose R, because we are choosing the R number from here. That's the number of how we choose R positive integers from the integers from 1 to m. Okay, so suppose alpha is an element in Q's of R and M, and beta is an element in Q's of S and M, S and N. Then we can define the following things. Say S is an m by n matrix over a field F. Then this notation A, alpha, and beta is a subset of A, submatrix of A, having the alpha rows of A and beta columns of A. So this submatrix is consisting of the rows from A corresponding to this alpha. So, and the columns of B, columns of A corresponding to this set beta. So this is a R by S submatrix of A. And this notation says the submatrix of A excluding the rows of A corresponding to alpha, the set alpha, and excluding the columns of A corresponding to the set beta. So this submatrix is a submatrix of A whose size is m minus r by n minus s. And this two are the similar notation with this bracket and parentheses. So this includes alpha rows and but not including beta columns. And this excluding alpha rows but including beta columns. Okay. With these notations, yeah, we can write the matrix computation in a much easier way. Okay, this is one other fact that suppose we have a block matrix, partitioned matrix like this. Then the inverse of this matrix can be obtained with this formula. When the inverse of A11 and inverse of A22 does exist. Okay. Okay, so when we deal with the large size matrix, if we have a proper information for the smaller size of submatrices, then we can use those information to get the information of the original big size matrix. Okay, that's the ideas. Okay, inverse of a small length adjustment. Yeah. So suppose the matrix B is A plus X R Y, then B inverse can be obtained in this way. And as a special case, when X is n by 1, then B1 can be obtained in this way. 이런 행렬. Okay, so the knowledge on the smaller size block matrices, submatrices of the original one can be used to understand and to treat the original large size matrices. Okay, determinant and determinant gain. Yeah, we have learned a lot on the determinant, many facts and theorems. This is the consequence of it. Okay, now we define the compound matrix. Compound matrix is a matrix that can be generated from a given matrix. Okay, so the compound matrix from case compound matrix from a given m by n matrix is a m choose k by n choose k matrix whose alpha j entry is determinant of alpha. It's bracket, not parenthesis, bracket and bracket. It is called the case compound matrix of A and denoted by CK of A. So alpha is a subset in here, the beta is a subset in here, with the strictly increasing orders. Okay, so for example, let A is this 3 by 3 matrix. Then C2 of A is a 3 choose 2 by 3 choose 2. So it's a 3 by 3 matrix whose entries are determinant of those 2 by 2 submatrix, 9 2 by 2 submatrices. Here, the 2 rows are chosen from as the first 2 rows of A, and this is the first and third and second and third rows. And here, first and second column, and first and third column, and second and third columns from the given matrix A. So this is the C2 of A looks like this. Okay, then this think about the properties of this compound matrix. Suppose A is a m by k matrix and B is a k by n matrix. Then this R's compound matrix of AB is same as R's compound matrix of A times R's compound matrix of B. Okay, and it also it holds the similar properties that we have seen on the matrices, such as CK of I is identity, and inverse of CK of A is the CK of A inverse. CK of A transpose is same as CK of A transpose of CK of A, and conjugate case compound matrix of A conjugate transpose is same as conjugate transpose of the case compound of A. So this is a generalization of the knowledges that we have known. For example, okay, and adjoint matrix and inverse the properties. This is the most well known as an equation equality. So I will show it. Okay, here first. For the compound matrix, you will be able to find the related information from the web resources, and here we supply some of the rigorous proof on the properties of compound matrix. So the proof on this R's compound matrix can be given in this way. Okay, so the proof shows the IJ's entry of CR of A times CR of B looks like this. Then we use Cauchy-Binet theorem that makes the summation of A's of this submatrix times the submatrix of this B becomes the submatrix of AB of this form. Then we can find the relationship between these two terms that lead us this relationship. But it's what says the conclusion that we like to find. Okay. So we now use the Cauchy-Binet theorem that we will introduce soon. Similarly, we show this relationship. All we have to do on this is just choose the off-diagonal entries. All the off-diagonal entries are 0 and main diagonal entries are 1s. That's much easier to show. And similarly, we can show the others one at a time. And one of the important facts related this compound matrix is this Sylvester-Franke theorem. Okay, so the proof of the Sylvester-Franke theorem which is very interesting. Here we use Searle theorem, so we change this the proof of this theorem to this triagonal matrix T. So all we have to do is checking the diagonal entries on T. So how many repetition can be made on this R's compound matrix of A. So this number, n-1 choose R-1, comes out from those repetition numbers that lead us this relationship, so that which end to this equation, which is the proof of this theorem. Okay, this fact was proved in 1952 from a research paper that you can find from this web address. Okay. In fact, you can check it by yourself by using some computational tools. So if you have matrix, then yeah, we can really compute to check the theorems nowadays. 자, okay, determinant again. The next fact is the equation for A inverse. The inverse of the given matrix A can be obtained by multiplying 1 over determinant of A times adjoint of A. And also, if we use this fact, then Cramer's rule can be proved easily. Here, this notation says the ith column of A is replaced by B on A. So, determinant of this matrix, whose ith column is replaced by B, over determinant of A is xi. Then we can obtain x1 and x2 up to xn on the linear system of equation Ax equal B by this formula, Cramer's formula, to get the solution vector x. I will show you the proof of it, and sure complement and determinant of other two formula. Here is the rigorous proof on inverse of the square matrix A. Okay. A inverse is the product of 1 over determinant of A times adjoint of A. Okay, this can be obtained from this relationship. Okay. Let's think about A times adjoint of A. Then A is a matrix whose entries are Aij. And Ij's entry of adjoint of A is the Aji, whose Ji entry is the minor, Ji's minor of the given matrix A. Okay, so the Ij's component entry of A times adjoint of A is the product of this row and product of this column, which can be written in this way. Okay. Here, we can use the Laplace cofactor expansion. Suppose for the case when I is equal to j, then this value is exactly same as the determinant of A, because it is the cofactor expansion of A with respect to the ith row. But if I is not j, then it is the cofactor expansion of A with respect of a certain matrix whose two rows are same, which implies the value of it is 0. So if you write it, then A times adjoint of A can be written in this matrix. The main diagonal entries are all determinant of A, and all off diagonal entries are 0. So we can write it as the determinant of A times identity matrix. Okay, so from the assumption, since the matrix A is invertible, so we can divide this equation 3 by determinant of A. Then 1 over determinant of A times adjoint of A is the identity matrix. Since A is an invertible matrix, if we multiply A on both sides, then A inverse goes to this way. So A inverse is now same as the 1 over determinant of A times adjoint of A. So this is comes directly from this comparison and the Laplace coefficient expansion. Okay. So you should be able to reproduce the proof. Okay, with this formula for the inverse of A, the theorem, Cramer's rule, can be proved. Okay, what is the Cramer's rule? Suppose we have this linear system of equation, Ax is equal to B. If determinant of A is not 0, then this system has a unique solution of this. Each xi is the determinant of this aj over the determinant of A. This aj is a matrix that can be obtained from A by replacing j's column by the vector B. Okay. Yes, like Mr. Yun said, we from this given linear system of equation, we can have x is equal to A inverse B because A is an invertible matrix. So this x vector is same as A inverse B, but we know A inverse can be written in this way. So this x can be written this matrix times this vector B. Okay, what it means is the the j's entry in this vector. So xj is same as the j's entry in this column vector, which can be obtained by multiplying this j's column times this vector B. Okay? So, what is this? Okay, so xj is same as a1j times b1 plus b2 times a2j times plus plus bn times anj over the determinant of A. Isn't it? Okay, this is it. All we need is to figure out what is this. We can easily find this is same as what was defined in here. Because, you see, here's B1, B2, and Bn's. This is a cofactor expansion on the j's column with B1, B2, and Bn. So this is a kind of Laplace cofactor expansion on a matrix whose j's column is a vector B, and all other entries are same as the ones in the matrix A. So it is this that if we write it in the terminology that was given in the theorem, then that's the AJ, the determinant of this AJ matrix, which is obtained from A by replacing J's column by the vector B. So this is same as this. So now we can write it as xj is a product, some determinant of aj over the determinant of A. This is the proof of Cramer's rule. Okay? Okay, now the review continues. Here, yeah, there are other properties of undeterminant. One is Sylvester's inequality. The more important thing is this Cauchy-Binet formula. This is the suppose C is a matrix whose matrix which is obtained by multiplying two matrices A and B. Then this Cauchy-Binet formula tells us the determinant of submatrix of C can be obtained as the summation of determinant of some submatrix of A times the determinant of submatrix of B with this gamma of cardinality R. Okay, the Cauchy-Binet theorem is important because this is the natural generalization of the multiplicative property of determinant, and also the determinant of the submatrix of AB can be obtained by knowing the determinant of submatrix of A and determinant of submatrix of B, which is a fascinating fact. The rigorous proof on those Cauchy-Binet theorem can be obtained in this website, and also you can watch this some more information from YouTube and others. Okay? So you may refer it. I think that will end today's class, and we will continue to finalize the linear algebra knowledge for the linear models. Any questions?